You made it here, so you're doing great. So far, so good. Oh, let me check. I don't want to be on mute today. And everyone confirm I'm mutable, so that feels good. Mutable. All right. So, I want to leave inverses in the past, or did I leave you with some task maybe? I can't remember. No, we just ended with the graph. Okay, great. So I posted an assignment for 1.6. Today we're going to start chapter 2, which is going to feel weird because it's back to linear equations, which are just straight lines, right? Y equals mx plus b type of stuff. So it's going to feel like, whoa, we already kind of talked about that. But now we're going to talk about it in more detail is all. So gonna kind of take it way back to, bookmarks. There. Linear functions. Right, so things that have the form typically mx plus b or b plus mx. Right. Linear functions just mean equations of straight lines. Equations of straight lines, which we touched on, but now we're going to build on that. Or dive deeper, rather. Let's start with an example, and I posted the chapter 2 examples on Moodle. I don't want to have I made little notes to myself which section was ending and starting. Whoa, where'd it go? Okay, there. Suppose you're running a coffee stand. Labor cost is $90 per day, and the per cup cost is $1.30. I feel like they're doing something wrong if the cost per cup is $1.30, but whatever. It should probably be cheaper, but it is what it is. And we are supposed to write an equation for the cost. Okay. So first thing we want to do is identify what the variable is for the cost function. Okay, it looks like the per cup, right? The cost changes per cup, okay? And so here, let's just call that maybe C, right? Cup, whatever. To avoid talking about the cost function, which is what we want to do, we want to write an equation for the cost, or maybe we can. Can we keep them straight? A capital C for the function and a lowercase c for the cups? That's confusing. How about just a function? So then we can write f of c a function of the number of cups. Right, which is how you're going to read this. F of c as a function of the number of cups. Okay, so now I know that my x is now c. It's just another name. Okay, and from the description, I don't think it's that big of a stretch to say that, okay, regardless of how many cups I sell, even if I sell 0 cups, right? What's the cost? it's going to be $90, right? You have to pay rent, you have to pay all these things. And so 90 is the cost even when selling 0 cups. Right, call that a fixed cost, obviously. And then the cost is going to increase by $1.30 for each additional cup that we sell. So what that looks like is plus, right, increase by $1.30 for each additional cup. And I'll include the plus, right? And then it increases by $1.30 for each additional cup, which we're denoting by C. Here, this is of the form, what color haven't I used yet? How about dark green? Notice that f of c equal to 90 plus 130c is of the form f of x equals b plus mx, which is a linear equation. Right? Mx plus b is usually how we, it kind of rolls off the tongue a little bit better. That's all. But usually what happens is we say it, so when we explain, right, 90 is the fixed cost, and then it increases by $1.30 for each additional cup. So that's how we usually say it. So here I wrote it to match. They're the same though, right? So this means that it's a linear equation. What's our job? Our job is to see a function like that and say, oh, that's a linear function because that's what it looks like, right? So, oh, can you imagine if I erased it? That'd be bad. We need to be able to recognize linear equations. So that's our job. We said m is the slope. We've already calculated rates of change, but let's go back there. That was fun though, right? I like that. Calculating rates of change. Let's see here. I'll nab this whole thing. It's huge. But we already said all of these things here. But he just says it in a better, cleaner way, I think. But it's everything that we just said. So a linear function is a function whose graph produces a line, and we can always write them in the form of b plus mx or mx plus b. They're equivalent, where b is the initial or the starting value of the function, right? Notice that we're relying on this fact that, okay, the initial point is going to be when x equals 0, right? And we're going to go back to that later, okay? But that's something to remember. And m is the constant rate of change of the function. And here he just explains how, so many people like to write the linear function in the form of b plus mx because it corresponds to how we talk about it typically. Right? The output starts at b and increases at a rate of m per x, right? And then he just explains that for this reason alone, we're going to use b plus mx as much as possible. But you can all know what you mean, right? And so it doesn't matter. But I think he's just explaining why he's kind of shaking things up. Usually we write mx plus b. Remember increasing and decreasing functions? What we landed on for increasing and decreasing functions, if I have a straight line, right, then I have two options, right? I can have my x and my y here. I'll draw my general graphs first. If I have a line that looks like this, that's increasing, right? And so here, the increasing, which means that the slope, right? If we talk about in terms of the slope, well, it means the slope is going to be positive, right? Rise over run, and you can confirm it, but I think we're at the point where we saw that and we said, okay, if the slope is positive, right, greater than 0, then we have this increasing function. Whereas if we have a negative slope, right, then we're starting at some point and then we're decreasing at the rate of change, right? And so then we have a decreasing function. Might look something like this. So this is decreasing, which means that m is less than 0, right? It's negative. I guess the third option, right? M greater than 0, m less than 0. What if m is 0? Now I have a 0 slope, right? Then that makes a horizontal line. X and Y. Oh, put a little bit of tilt on there. That's not what I wanted. Doesn't help that my axes are all, but here, a horizontal line means that the slope is 0. Thinking about the slope, right? It's going to be the rise over the run, right? And so if you think about the rise here, well, it's positive and then the run is positive. Whereas here, the rise is actually negative over a positive number, yielding an overall negative, right? And so that's how we get these. But the reason this is 0 is because the rise is 0, right? 0 divided by any distance is still going to be 0. Okay. Nice. All right. Let's do an example. Before I get ahead of myself. So if the value of a car depreciates over time, according to this equation here, so we've got the value over some as a function of time. Now we're not told what the units for time are, so I'm not going to specify. I'll just take it as it is. It's reasonable to think that time is maybe in years, right? But it doesn't say, and it doesn't really matter for the math side, unless you were given the units in something other than years, then you'd have to convert it. But we're not there yet. All right, so we've got the value. This is the value function, value as a function of time. We have to interpret this. What would we have to say? what was the initial value of the car? So we all understand how depreciation works, right? You buy a car, you take it off the lot, ding, ding, ding. It's just worth less and less and less until it's worth very little. Right? So the initial value of the car would have to be this 13,000, right? And so can start there. The initial value, oh boy. Got a frog in my throat. Uh-oh. The initial value of the car must be $13,000. I'll put the comma in there just for readability. Right. Now, we see that we have a negative here, right? Which means we have a decreasing function. Decreasing function. And the value, right, which is what we're trying to find, the value starts at 13,000 and then it decreases by this much, right? 2,000. So decreases by $2,000 for every t, right? I won't get specific. For every, you know what, but I will get technical. There's a difference. For every unit increase in t. Right? I needed to leave myself more space here. Decreasing by $2,000 for every unit increase in t. Why did I rephrase it so I'm relying on the definition of the slope, right? The definition of the slope is that for each unit increase in x, right, we're going to see a slope increase, but then if it's negative, it becomes a decrease, right? A slope decrease or increase in the overall output, right? And so here, note the slope is maybe I should say in general. The general definition of the slope, interpretation of the slope, there. I'm getting there. Interpretation of the slope, which we usually denote by m, is for each unit increase in x, just generically, we will see a an m, a m, I don't know, a m unit English, who knows? We will see, I want to say an m, but I feel like that's wrong.
Yeah, M is wrong.
A is correct. I know, but I feel like colloquially, I'd maybe say it wrong. A m unit, we will see a m unit increase in the output f of x. Yeah. So that's the general interpretation of any slope, right? Whether so if m is negative, let's say -4, right? Then we can still say for each unit increase in x, we will see a -4 unit increase, right? It sounds weird, but it's always safe to say that, right? Because what's a -4 increase? It's a 4 unit decrease. But notice how when you drop it and change it to decrease, then you have to drop the negative. And so for me, when I want to play it safe, I just say a -4 unit increase. Sounds weird, but it's technically correct, and I'm not at risk of tripping myself up or anything. And then in the output of f of x. Nice. And what's the general interpretation while we're at it? The general interpretation of the intercept B in y equals, oh, sorry, I'll use f of x. But you can interchange them, right? B plus mx, matching that. How Lippmann said he would do it. The output is going to be B, right? When x is 0, right? And so the interpretation of B then is B is the output f of x when x is 0. Which means that f of 0 is B. Okay. Nice. This is a lot, but we've already seen it and done it. So now we're going to do more. So given two values, so if we're talking about the rate of change is the slope, right, of a linear function. So here, the slope of a linear function, given two values for the input, x1 and x2, well, that's fine. We were using A and B, but now kind of more technical, x1 and x2, but that's fine. And two corresponding values for the output, y1 and y2, or if we want to, right, x1 corresponds to an output of y1. So in coordinates, we can say x1, y1, right? And x2 gives an output of y2, which we could write in coordinates as x2, y2. If we want to find a linear function that contains both of these points, then how we're going to find the slope is the change in the output, right, over the change in the input, which is just a fancy way of saying, or maybe it's not that fancy, rise over run. You might remember, right? Change in the output is the y, so the change in the rise, and then change in the input is the run. If I have just a general function like this, and if I give it x1 and some value x2, we're told that the output here is y1 and the output here is y2, right? If I tasked you with finding the slope here, right, just using rise over run, I would say, okay, well, this is the rise, right? So here, it's the rise over, this is the run, right? The change in the input, which is the slope, right? How do we find this? If I had to calculate with values, right? This is going to be y2 minus y1 is the rise. So that's where this y2 minus y1 came from, right? And then the run, well, I want to find this distance. So I'm going to take the bigger value minus the smaller value, x2 minus x1. So it's the change in the input. Now I'm glossing over these deltas, but you guys have probably seen deltas in other courses, right? Delta is the change. So delta is the change. Delta y is the change in y. Delta x is the change in x, right? These are all equivalent, right? So whichever one you like is good. So here, right, the rate of change of a linear function is also called the slope of the line, which is what we said here. So the slope of a linear function, we can find rates of, so the reason I'm particular here about the linear function is because we can find rates of change for other functions, right? X squared, it starts off and it's not changing very quickly, and then it's changing very quickly. So then it's not quite the same. But we're just talking linear functions for now. So then it's the slope. We could also rewrite, right? y2, I can replace it with f of x2, right? So y2, we can replace it with f of x2 if we have a function. y1, I can replace it with f of x1. And so we could use this function. And this is the one that I would probably resort to the most. They're all equivalent, but that's the one that I'm going to use, right? The change in the output over the change in the input. Okay. Good. So let's do some examples here. The fun thing about straight lines is you only need 2 points on the line to know everything about the line. In fact, you only need 2 points to draw a straight line, right? If you have 2 points that are on the line, then you can connect the two and extend the line, and you did it. All right, so 2 points give us everything that we need to find the equation of a line. So we want to find the rate of change, which is the slope, between -2, 3 and 4, 0. How I'm going to write this is I'm going to rewrite this as functions, right? Or I guess what I should start with, mostly because I remembered I have a function example, so I don't want to make them the same. So let's use this version of the slope, right? Remember, they're all the same. And so if I identify x1, y1, and x2, y2, then the slope is going to be y2 minus y1 over x2 minus x1, right? Just from up here. You don't need that, but just to see where it came from. All right, so now all I need to do is map these outputs and inputs into this formula. Y2 I said was going to be 0, right? Y2 is 0 and Y1 is 3. So minus 3 divided by X2, which is 4, minus X1, which is -2. 4 minus -2. All right. Now I have -3 over 4 plus 2, right? Negative times a negative makes a positive. And so now I have -3 over 6. You can reduce that and your calculator will just do it automatically, but I'm just going to leave it as -3 over 6, just in case I don't want to trip myself up. I know this is where I landed, and that's going to behave the same as if I reduced it. All right, you can convince yourself of that. So now we have the rate of change between these 2 points. So we found the slope between these 2 points, which means if we have a linear function, the slope is going to stay the same for any 2 points. All right. Let's do another example. Here's the one where we're given the outputs. So the rate of change, given that f of 2 is 3, which means what? It means that x1, let's call it, right? Because it's the first one. X1 is going to be 2, right? And when I give an input of 2, I get an output. F of x1 is 3. All right. So here, x1 is 2, which means that f of x1 is 3. Here, x2 is 4, which means that f of x2 is 7. Using my personal go-to formula for the slope. Copy. I'll sneak it on this page and do the work on the next page. How about that? M is f of x2 minus f of x1, right? The change in the output divided by the change in the input, x2 minus x1. We already identified all the key players here, so it's just a plug and chug type of situation. F of x2 is 7 minus f of x1, which is 3, divided by x2, which is 4, minus x1, which was 2. Putting me at 4 over 2. I'm going to save myself some fractions and reduce that, right? Because I can see that it's 2. Right. But so sometimes I reduce and sometimes I don't. Wow. I do whatever's easier for me. And you should too. All right. So now we know the slope between these 2 points. Right. Got another example here to really seal the deal. A word problem. Which people don't tend to like that much. To read this, but what are you extracting? You're extracting the change in the output and the change in the input, right? Or at least the outputs and the inputs, right? And so here we go. The number of students grew from 4,000 in 2008 to 43,000 in 2010. If we assume the number of students is growing linearly, find the rate of change. Okay. So here, they don't specify how they want the input, but what's the input going to be? The year, right? And so I'm generically going to call this, so here the year is the input, right? We're told what year it was, 2008, then the population or the number of students is 4,000, the output, right? It would be kind of unreasonable to go the other way, right? Oh, there were 4,000 students there. What year was it? Right? And so that's why you want to kind of check in with yourself. Does that make sense? No, it doesn't. Right? And so the year is the input. And so from 2008, that's X1, to 2010, which is X2. All right. We've chipped away at 2 of the numbers, so that feels good. The number of students is the output, which corresponds to some input. So 4,000 is going to be f of x1, and 43,000 must be f of x2. You can write them as coordinates if you want, right? 2010, 43,000, or I guess I should start with the lower one. 2008, 4,000. Or 2008, 4,000, and 2010, 43,000. I don't use the coordinates that often, right? I'd rather use the function notation, but that's my preferred way of reading it, right? Maybe if you like the coordinates, then that's great. Okay. We wanted to find the rate of change, the slope. M is the change in the output, f of x2 minus f of x1 divided by the change in the input, x2 minus x1. Already identified all those things. So now we plug them in. F of x2 was 43,000 minus f of x1, which was 40,000, divided by x2, which was 2010, and x1 was 2008. Yes?
F of x1 be 4,000 instead of 40?
Whoa! Yikes. Yeah, absolutely it should. Oh, but I did it right. I'm surprised I did it right here. Okay. In my head, it was 40,000 the entire time. Makes you wonder why I would write 4,000. Thank you. Anything else I missed? I will say, so after I've made a little typo like that, typos aren't going to cost you very much on a test, for example, right? We're here for grades, I know that, right? And so typos don't cost you anything. So just outlining and identifying these values, telling me what function you're about to use. The math, we use calculators and you know, we slip up and we type the wrong number and stuff like that. So I don't obviously it's nice if you plug in the right values, but if you did a slip up like that, 40,000, I would say, well, I mean, you just told me that it was going to be 4,000. So you knew what you were wanting to do, right? And so that's part of the reason, well, I'm just a slow marker, but also it takes me a long time to pick apart, was this a typo, were you on the right track, right? And so that's just a side note. Typos, I usually take like half a mark off or something. But then as long as you follow through and you use that value and you stuck with it, that's important, right? Then you can have the rest of the marks, right? It's when you start flip-flopping and not following through with what you said, f of x1 was, for example, then that's bad. Okay. Well, I don't know what 30, is it 39,000 divided by 2? Who knows? But it probably reduces to something reasonable. 15 plus 4, 19 and a half. And the crowd goes wild. Just needed some time. All right. Good. What if, now let me just scroll through here and just make sure I didn't forget anything. Okay, I didn't. How do you know, Emily? I know, I just know. And if I did, you'll never know. What if we have 2 points and we want to find the linear equation that passes through these points? Okay, we know how to find the slope between these 2 points, right? Which is also the slope of the general line, right? So now we want to find the linear equation, right? Which is f of x equal to b plus mx. So I'm going to say step number 1 is find the slope, which we just did, right? I've got x1 is 0 and x2 is 3, and f of x1 is 3. Oops, I didn't write it out for the other ones. And f of x2 is 9. So I can find the slope. M is f of x2 minus f of x1 divided by x2 minus x1, which is 9 minus 3 divided by 3 minus 0. Phew. 6 divided by 3, I'm going to go with 2. Okay, so we've got the slope. X is just going to be held X, right? The whole point of the linear function or the linear equation is I can put in any value of X and find the output f of X, right? So X is just going to stay X. So the only thing I need to solve for now is the intercept, which is B. Now, in this case, right, as long as we remember that the intercept is I'll say step 2, find the intercept. The intercept is the output when X is 0. The output when X is 0, which in this case, it's a baby example, right? I have the output when X is 0, right? Which means that here we're given 0, 3, which means that x equals, so if x equals 0, f of x equals 3, which means that the intercept is going to be 3. Putting that together, should I use better color schemes here? Right, therefore, f of x is 3 plus 2 times x. Which we can confirm on Desmos if we want. How are we going to confirm it? 3 plus 2 times x. It gives me the values of the intercepts, right? 0, 3 is on there. That was one of the conditions. And now I can't remember what the other point was. 3, 9. So what I'm going to do is I can take, oh, I need to zoom out. What I can do is I can tap this line and I can chase the 3. 3 there. I can't screenshot that because it's very finicky, right? But I can confirm that 3, 9 is indeed on the line, and that's a good thing. And maybe I'll do this. I'll bring it in, but just tiny, just as a reminder that that's what we did. Whee! Yeah. Nice. I'm going to leave you with an example to do for, and we'll pick up here. Oh, see you until Wednesday. I know. How sad. But I think you guys are ready for a break. How about A and B instead of A and A? For Wednesday. And then we'll start there. Have an awesome long weekend. Followed by another long weekend. I always post the notes. Any questions besides that? All right. Blink and you miss it these Fridays.